This morning's session is SecSi Product Development Techniques for Ensuring Secure Silicon Applied to Open Source Verilog Projects by Joseph Fitzpatrick.
Hello. You came, SecSi product development. I think that's what I would call it, but you know. I had to encode it so it slipped by any reviewers. This document is not actually the preliminary revision. If you go online, the one that is there will be, and I'll throw this final one on my website sooner or later. I'll jump right in with who am I. My background is electrical engineering. I did a lot of focus on computer science and InfoSec as well. I spent 8 years doing security research, speed path debug, tool development, and stuff for desktop and server CPUs. That included hardware pen testing of CPUs for security's sake. I also did a lot of training. The company I worked for had lots of employees who did functional validation of silicon projects, right? You know, does it work? You know, the standard test plan, test every item in the test plan, and check a box and ship a product. I did some basic security training for them, which you know, I found that a little bit of security information goes a long way for someone who is deep down in the hardware and used to, you know, if it works, it works. If it doesn't work, do we really need it to work kind of mentality. On the side, I've been doing some research on low-cost side channel attacks as well as PCI Express attacks. If you're hanging around on Sunday at DEF CON, I've got a cool little demo of a PCI Express device that can do driverless DMA access to your system. It's lots of fun. And also, I've got a class, software exploitation via hardware exploits. We just taught it the past 4 days here. I see a few of you here who just enjoyed that class. I teach that with Stephen Ridley. He's company, Sipiter, teaches and runs that class privately if you're interested. Enough of shameless plugs. I'll give you an overview of what I'm going to talk about. I'll start out with kind of a definition of what hardware security means to me, because there's kind of a lot of different definitions and different things that it means to different people. I'll mention a bit about how hardware is designed, for those of you who are not familiar with that. And then I've got 3 projects. OpenRisk, which has some JTAG issues. OpenMSP 430, which uses some sketchy case statements. And Amber, which has some memory aliasing stuff that I found. And I'll summarize all of that. So these are all my definitions. You don't have to agree with them, but this is the context for which I'm going to be talking. Physical security is not hardware security. Physical security is keeping people away from things. In my mind, hardware security is, okay, we have physical access to the device. We assume that, is the device secure? Supply chain security is not hardware security. Supply chain security is going to tell us whether the device we have is the one that was designed, right? That's helpful to know, but once you get down to it, whether you have a secure supply chain that is, beginning to end only designed by, secured, vetted, security clearanced, U.S. citizens, it still takes firmware updates and runs code no matter who wrote it. Secure boot is not hardware security, right? Secure boot is the process of saying, oh, well, we have something in hardware that tells us that we can trust the software running on our system. Again, secure boot is something that depends on hardware security, but it, in and of itself is not itself hardware security. And finally, secure firmware is not hardware security, right? Secure firmware, in mind, it's the old argument, software people call firmware hardware people call firmware software. So I'm going to call it software for the scope of this presentation. So again, hardware security in my mind depends on all these things. We need physical security, we need supply chain security, we need software security, we need firmware security in order to scope and know what where our goals are for a secure hardware. So hopefully this doesn't disappoint anyone. If you play Taboo, you get a word that you have to get the people to guess, and you're not supposed to use any of the other words. So these are all the things I'm not going to talk about. So if you're coming here looking for formal verification, encryption, firmware, security ICs, or security engine IP blocks, I have no information for you. I apologize. My focus is like, okay, we have lots of people who are already doing functional validation of hardware. These people need to know a little bit more about security so that when they do their functional validation, they can think about security in the process. Everything in here is all just RTL inspection stuff. So I had a bit of a challenge. How many of you here know what Verilog is? How many of you here code Verilog regularly? Okay. So it's Black Hat, right? It's an InfoSec conference. How many people at an InfoSec conference really know what Verilog is and code it? Very, very, very few. But at the same time, how many people who come to Black Hat and know what Verilog is are going to be in this room? Probably all of you. So please don't heckle me too bad. I am no Verilog expert. I've never actually written much Verilog, but I have looked at lots and lots and lots, and I see the same issues over and over again. For those of you who are not familiar, Verilog is a hardware description language. It's a way of defining hardware, right? Software programming languages, you're writing code that runs on hardware. Hardware description language, you're defining wires and gates that hook up and do things. So programming languages, they make programs when they're compiled. They break down into functions and procedures and libraries, and they end up being a sequential list of instructions for the most part. You know, there's exceptions and fancy architectures that do other things. Hardware description languages, on the other hand, you're making hardware when you synthesize it, right? You break this down into modules and IP blocks, right? And they're basically a set of assignments that all kind of calculate in parallel. So our second slide, to give you an entire background in Verilog, is a seed example and a Verilog example, right? This is a simple sum function. We have A and B and C, and we want to add them up. And please don't critique me on the quality of either code. In C, we come up with some temporary variables. We add A and B into one temporary variable. We add our temporary variable and C into another temporary variable, and then we return the value, right? The result is we get back the sum of those three numbers every time we call it. In Verilog, on the other hand, we make a module, and this module has A, B, and C as inputs and sum as the output, right? We don't have variables per se, so we create a wire, and then we'll assign sum to temp2 to C plus temp1, and temp1 to A plus B. And those of you who are C-minded people are going to freak out because none of that works, right? Well, that's what I'm saying. Everything's in parallel, right? It doesn't matter what order we put these things in because they shuffle and they just work. Just make sense? Of course, I'm going to go show you a whole bunch of examples where it doesn't work. So we'll start off with OpenRisk. This is an open source Verilog CPU. Are any of you familiar with OpenRisk or open course projects? Okay, some of you. Any of you work on them? Am I critiquing any of your work? Good. Just curious. You never know who's going to be in the audience. So OpenRisk is great. It has pretty good Linux kernel support. It used a lot in academia as an example instruction architecture. It's actually used in some commercial products. It works well on both FPGAs and it has been synthesized and again shipped in commercial products in even the recent past. It's used in what's called the OpenRisk Reference Platform System on Chip, ORPSOC, which is what I looked at in particular. Before we jump into that, I'm going to give you a little primer on what state machines are. How many of you know what a state machine is? How many of you know about JTAG? Okay, this will be easy. Again, a state machine, you have a bunch of state. In this case, you have 16 states that the logic could be in. The state is stored somewhere in a register, and you basically have this diagram that tells you how to jump between different states, what conditions have to be met. So it's not defined on here, but basically if you're in this test logic reset state and your mode bit is 0 the next time there's a clock, you move to this one. If your mode bit is 1, you just stay right here. Okay, so if you're here and your mode bit is 0, you stay here. If it's 1, you move into the next state. So basically by toggling a mode bit every time the clock switches, we can jump from state to state to state to state and do different things with this state machine. JTAG, if you're not familiar, is a way of getting some debug access to a chip. Basically, fundamentally, you use this shift DR and shift IR state to shift data in to the chip and shift data out of the chip and shift instructions in and out. More details, you can read Wikipedia and you'll get a nice primer on it. So something that's common is a one-hot state machine. What this means is instead of, if we have 16 states, you all know we can encode that into 4 bits, right? Just having different states. Well, for reliability and other sakes, it's nice sometimes to have a single bit for each state, right? That means all the other states are 0 and one bit is set as a 1. So here we go. We look in the code. We can see the definition of each of these states that match to each of these states. So each one of them is a separate register. And then we want to look at how the next state is calculated. In this case, what they did is they came up with a little logic block for each state. So the test logic reset state right? And this state, I'll decode some of the Verilog for you, always means that, basically this event is triggered whenever any of these signals change, either the T clock signal or the T reset signal, right? So when we reset the part, it resets. That makes sense. When we have a clock, every time we have a clock, we might jump to the next state. Then based on, if it's in a reset state, we'll set test logic reset to 1. If we have another reset condition, we'll set reset to 1. Otherwise, we'll check the previous state. So if we have TMS of 1 and either of these states, we're going to go into 1. Otherwise, all other cases will go to 0, right? So this logic is going to be calculated every time there's a T clock trigger, right? And it's going to set the new, what's it called, test logic reset state. Just below it, you see the run test idle state. And again, there's a block of logic that gets triggered every time there's a clock and assigns the new value of the run test idle state. So I'll get into a minute. Basically, this is kind of an interesting way of architecting it because there's nothing there checking to see if it's one hot, right? We basically have 16 different state blocks of logic that each calculate 16 different bits, but no one's really checking to make sure the other bits are right. Excuse me. So these cores can be implemented inside a bigger system on chip that you might have. They might be actually synthesized or implemented on a chip, and all these are external signals. So let's look around and see if there's any of these states that we can actually tamper with from another signal. If we look, a couple of these pins are output. The reason they're output is so that other parts of the CPU can monitor them, behave based upon them. Luckily, in this case, there's no inputs. That would be a red flag. Basically, if we could from somewhere else go and poke and set one of these bits, that would be a nice way to make it no longer a one hot state machine. What I did find is pretty interesting is this one state, run test idle, has this really long stream of logic, right? We have 4 values and actually a 5th value. Logically combine all of them to tell us what our next run test idle state is going to be. When you synthesize this, there's a lot of optimization that goes on, so it may not look exactly like this. It may look bigger or smaller. But if we're going to put this on an FPGA, again, this is an old FPGA, what happens is you have these lookup tables. And the lookup tables basically are a map. For any of these 3 inputs, you can come up with any output, and you, as the FPGA designer, define what any of those outputs would be. Does that make sense? So we have essentially 5 inputs here. We don't have 5 inputs here. So the way this would be synthesized in very simple terms is basically we take 2 different logic cells and cascade them. So we put 3 inputs here, carry the output to another logic cell, and put the other 2 inputs. Right? This is the only state that does that. All the other states only have 2 or 3 inputs to this logic block. What that tells me is when we synthesize this, we might actually have a longer delay on this one than all the others, right? So this opens it up for glitching, right? What's even better is JTAG is usually externally user accessible pins, right? And we control the clock with JTAG. So basically, if we wanted to, we could probably figure out a way to glitch this to inject an extra bit into this state at any point in time, right? There's nothing in the entire logic that ensures that we're one hot, right? So we could be over here, in exit 2DR, right? And we glitch the T clock. Exit 2DR works fine, but run test idle ends up with the wrong value, right? Then as we shift through states, we can have this other state that's following a state behind, right? And so we might have both select DR and select IR selected at the same time. Then if we go through with the right states, you see that these 2 chains are parallel. We could actually end up being in shift DR and shift IR at the same time, okay? I don't have like a fancy exploit that this is going to like end the world, but this is the kind of bug I've seen over and over and over and over again that we can do something that the chip isn't defined, that isn't defined for the chip, and no functional tester would ever really think about this. So let's look at what happens if we did that. Luckily, they used much cleaner looking logic, in my opinion, to define what TDO value is going to be. Basically, if we're in shift IR, then we do IR output. Otherwise, we do something else. I think I accidentally clipped off more code. Otherwise, we're doing TDO out. So it's they kind of covered their bases here in making sure that this scenario, which should never happen, we might be able to cause to happen, will be taken care of. So what if DR had precedence over IR? Would that change how this would make sense? What other functions of the chip respond to JTAG state? Remember, I showed you we output the shift DR, pause DR, update DR, and capture DR tap states. So other stuff in the chip can be triggered on these states. What happens if that stuff is triggered at the same time as something else? Particularly update DR and update IR. What if these modes collide? What if these two modes cause other things to collide on the chip, right? So again, there's a bit of theoretical scenario here, but this is how these bugs start, and you just kind of roll down the hill, seeing the implications of all this undefined behavior. Just peek at my time. So you guys remember One Hot or Not, the website like 10 years ago? So we're gonna do a little one hot or not, right? So if you take a peek at this block of logic and tell me, do you think this is one hot or not? Those of you who are not familiar with Verilog, I apologize. This is probably not going to be easy. Basically, what we have is a case statement down here. We have a bunch of X's in our case statement. That's kind of a practice that's hopefully going to die very soon. It's going by the wayside. But what happens is we say, okay, if these last 4 bits are true, then this is our new state. If these last 4 bits are these values, this is our next state. If the first bit is this value and we haven't already assigned something, this is our next state. And if the first bit is this is our next state. Otherwise, this is our new state, right? When you have an X, it means either don't care or don't know. And the difference is actually important here, right? If we have this assigned to a bunch of X's, it's a don't care, and that means that our state might actually end up being not one hot, right? When it's not one hot, then we run into problems. So here's another example. Take a peek, those of you who are playing along. Is it hot or not? One hot or not? So in this case, there's a lot more logic, a bunch of ifs with cases, but what we don't have in this case is a default case. So basically, you'll trickle down, and if we get into one of these case statements and there's no default, then there's no definition of what's going to happen. In most cases, that means it'll just retain the previous value. But again, when you're optimizing and you're synthesizing, different software might interpret that differently. You might actually get a don't care that gets generated in there. And finally, this is hot or not, one hot or not. This is one hot. We've put basically a default case into every single one, and we've defined what the default case is. Basically, whenever state gets screwed up, we set it back to this one state. So even though we haven't protected against state getting mixed up, at least we have a recovery plan in place. So as a bonus, to throw in this extra JTAG bug, the ID code select, so when we're in shift DR, and ID code is our current instruction, what it tells us to do is basically shift data out and shift in, shift data out and shift in a TDI bit, right? So basically we shift through the 32 bits of ID code. The problem though is down here, basically any other time except for shift DR, we reset our ID code. If we go back to the JTAG state machine though, there's shift DR, which is when we normally spit data out, but we have this pause DR state. The purpose of the pause DR state is to take a break. So we shift 8 bits, we hang out for a minute, catch our breath, we go back, we shift out 8 more bits. In this implementation, we're not going to get 8 bits and another 8 bits and another 8 bits and then the last 8 bits. We're going to get the first 8 bits every time. So again, nothing really you can do with this specific bug, but when you have this on something that's a key, when you have this on something that's a shifted in value, taking advantage of this pause DR state can be really fun sometimes. So on to MSP 430, as I think I'm actually coming close to running out of time. Oh, no, I got 10 minutes. So OpenMSP 430 is an open source Verilog CPU. It's a clone of TI's MSP 430. It's binary compatible with all the standard MSP 432 chains. And it's much simpler than OpenRISC. It's just a simple microcontroller. For those of you who aren't familiar, we've got a front end and a back end, right? The front end is what grabs the data from memory and sometimes does decoding of it and hands off what needs to be executed to the execution unit, right? So these are 2 separate blocks, 2 separate modules. In this case, they have 2 separate state machines. This is kind of messy code, but what's good about this code is actually it's very well defined. You have every single thing defined as including a default. Like if anything else happens, just go into this state. So we know what's going on. What I found interesting about this is this always at block, right? This is the sensitivity list. Whenever something in this block changes, this whole state machine gets triggered. What's not in this is a clock, right? So this state machine is not triggered by a clock. It's triggered by a list of signals. Hopefully all of these signals are synchronous signals, But can we tell that just by looking at it? No, we can't. So let's look at these signals and see if there's something we could, as an end user, an outside user, someone who has access to external pins, can trigger. And what stands out to me is actually this CPU halt command. Because if we look at what feeds into that, we have this debug halt command spitting in there, right? That debug port can be attached within the SoC to another device within Verilog, or it could be an external pin that might end up being user controlled. So let's go back and look at debug halt command, right? There's actually a bit of logic behind it, but what it comes down to is we're triggered on debug clock or debug reset, right? So if we can control either of these signals, we can toggle the front-end state machine, and the back-end, the execution unit actually uses these signals differently. So we have two different state machines using two different triggers to clock. So basically what happens if we toggle debug reset, right, it can change debug halt command. If we change debug halt command, we can change CPU halt command. If we change CPU halt command, even if nothing else changes, we trigger this block and we reevaluate, and we could hop to the next state. And when we get out of sync with our backend, that makes bad things happen. So is your state machine strictly clocked? Are all the sensitivity list parameters actually synchronous to the same clock? And are critical signals pure and not combined logically with other user-controlled signals? If you have a system-wide, secure mode on, secure mode off bit, is that the one bit that you're using, or are you using secure mode on and some other user-controllable bit? So let's scoot right through. Amber is the last one I looked at. It's an open source Verilog vCPU that's an implementation of ARM v2. ARM v2 is an old instruction set that's not well supported anymore. You can use it up to Lynx 2.4, and some people have patched later versions. It's much more complex than MSP 430, but it's still no native memory controller like OpenRISC. So what I looked at here was the memory map, which was interesting. This is basically a bunch of things that live in the memory. We've got our main memory. We've got a special cacheable boot memory. We have modules that are memory mapped devices: timers, interrupt, 2 UARTs, Ethernet. So these things, these extra pieces of hardware are mapped into the memory interface. So let's take a look. How do we, actually one last thing. Down at the bottom, we have this little function in UART0, basically a macro that will let us know if we test an address where it's located. So we basically, when we want to decode an address, we use this function and we test. Is it in Ethernet MAC? Is it in boot memory? Is it in main memory? If we somehow misconfigured something on the back end, this would let us know the hierarchy, what's decoded first. What's also interesting is the final default case, we default to main memory, right? So if we access an address that's not defined anywhere else, it takes us to main memory. So even if it's not in main memory, it'll take us to main memory. What can we do with that? If we look at how memory is accessed, we see this nice little comment that tells us exactly what will happen. Wrap the address at 32 megabytes. So this is an issue I've encountered many times, right? When you wrap an address, right, that means even if you have a gigabyte of memory, you have basically a whole bunch of copies of your 32 megabytes of memory. That's not so bad. It's something that was pretty common practice in embedded systems for a long time. But what happens if you are protecting a piece of memory, right? If you have a security mode, a security bit, a privilege level that depends on you being a super user to access a byte in memory, does that protection protect against the address, or does it protect against the aliased version of the address, or the 15 aliased versions of the address, right? It's a way to bypass a memory protection, right? So what devices live in this memory map? How are they allocated, ordered, and prioritized? If there are multiple implementations of address decoding, do they decode overlaps with the same priority, right? If you have two different devices on a bus, they might each have their own address decoding as to where they send things on the bus. Is it actually identical? Can you take advantage of that? And finally, do aliases exist? Can these aliases be used to access a byte of memory that is protected if you were to access it as another address? So as a summary, we talked about some unchecked state encoding, untested state untested state transitions, very permissive sensitivity list, obscured signal combinations, and then aliased, overlapped, or misprioritized memory maps. And that's what I got. Any questions? Did I bore you? Oh. Uh-huh. Yeah, that's what's nice about VHDL. Verilog is like a, yeah, it was never designed for synthesis in the first place, so when you're using Verilog, you can do a lot of stuff that you don't get errors or warnings out of that I think should get more errors and warnings, like you assign things that are different lengths, and it just fixes it for you. Yeah. That's why I'm focused on Verilog. It's easier to make bad code. Yeah?
So a quick question, since I'm also working on the area. So the point is that when you go through synthesis, different things are true and different kind of string file cause different results. Which means that if you identify the vulnerability in this Verilog level code,
yeah.
you may be exploited the same vulnerability in the physical device because you don't know how they synchronize this one.
Right.
How do you do the same thing, how do you tracking the Verilog level vulnerability into the physical device?
So how do you map it into a physical device? So what I always did is, when I was doing my RTL inspection, I'd go and I'd find all these interesting things and fix whatever is just blatantly bad. And there are things that, like the glitching the T-clock, right? I don't know how it's going to be synthesized, right, for an FPGA or for an ASIC. But I know that there's something interesting there, and so I put that on my list of something to test as a hardware pen tester, right?
Have you tested your hardware level, like how you explore this?
Yeah, a bit.
Like FPGA or ASIC?
On ASIC. I've done a little bit on FPGAs recently, but mostly ASIC.
I see. You show us some.
No, that was at my prior employer. So again, I used to do this on ASICs, and I realized after about a year of not looking at Verilog, I should keep my game up. So I started browsing through open course projects and said, there's nothing major, nothing burning here, but what I'm seeing is the same coding errors or oversights that I saw a lot of otherwise. So I figured I'd pick them out, and since no one's really talking about this, I figured I'd talk about it. No problem.
So have you ever tried to contact any company for like commercial versioning? Because I know people using the free code through the open course, for example, and they would also like modify them to make their own like commercial version. Have you ever tried to?
No. But if they wanted to pay me, I would do it. Yeah, I haven't. I know that all of these projects are sometimes used in commercial projects, and I'm sure I modify them, and I'm sure that the stuff they actually make looks different. So.
Actually, on the same thing, have you considered looking over at the net FPGA code?
Not yet.
Because a lot of educational institutions use that to teach people how to do routers and switches.
Net FPGA? Oh.
Yeah, and so I think we've got an entire generation that's being trained on that code, at least for doing this sort of stuff.
I will.
It's all open source. There's like reference implementations of routers.
Actually, I got started on this because I've been playing with OpenRISC and actually like trying to synthesize ORPSOC. Yeah. So I'm trying to synthesize ORPSOC on a Xilinx digital and Atlas board, and actually get it set up so I can do some like hardware pen testing on that. Okay, and more expensive. You got a question? Sorry. So I've only covered code reviews. Here, there's a whole mess of different things that you could do. You could, basically what the procedure I ended up doing is, I started out using manual inspection, and then I realized that there's just certain structures that always have issues. And so I just came up with a list of greps of the code that would find all these critical areas, and then I'd go and manually inspect them. I never get so far as making my own tools to automate that. There are tools available for doing like tracing signals back. I don't know what proprietary tool set you may or may not use, but basically tracing paths of logic. You can look at the Konov logic. If you have something that's supposed to be a secure signal, trace it backwards until you find something that's not in your list of secure signals. Yeah? I used to say no, not that I know of, but yes, there are. Are there any static analysis tools? So for security purposes, Jasper Gold, I'm not familiar with it. I've never used it, but when I answered that question previously, people told me to check it out, and I haven't yet. Maybe I'll get in touch with them and tell them to send me a free copy. Could I do something coherent or a denial of service if I tried to exploit these things? Yes, I think that something coherent could come out of these. The most interesting one I'd say is the aliasing bug, right? Again, this is a simple architecture. There's not really any security protections or super user modes, but finding that same bug on a multi-ring chip, that's money. And the JTAG one, again, this example was no real exploit that I came up with. Again, I'm talking about RTL level. I'm not talking synthesized. I'm not talking about real chips. Once you get the real chip, though, the same logic would apply. You find a one-hot state machine that you can glitch into multi-hot state. You've entered into undefined territory. It depends on the chip and how it's implemented if that lets you do something bad or not. Again, a black box scenario, this gets really hard really fast. So, any more questions? Okay. Thanks very much.